Thank you. So let's continue from yesterday with nonlinear tomography, especially electrical impedance tomography. So yesterday I showed you a few things, few applications for EIT, electrical impedance tomography. And this is one of the maybe situations to keep in mind, that there is a round object. Well, this is a 3D object. This is kind of a 2D definition. There is an approximation there for sure, because the current will go in a 3D fashion. But in practice, this is a surprisingly good way of approximating. So in this talk, I will talk about two-dimensional imaging. So let me skip past the... Oh, mic on. Thank you. It's so hard. First of all, remember to wear it, and then even put it on. Okay, better. Good. Okay, so these we saw already. So let me explain a little bit about how the EIT measurements are collected in practice. So one thing to keep in mind is that we collect several measurements. In this case, this is a tank built by John Newell at Rensselaer Polytechnic Institute. Here you see these metal squares around the tank. So the size of the tank is like 32 centimeters, so it's something of this size. These metal parts are electrodes, and they are separated by an insulating rubber piece. This here is salt water, or saline. These things are made of agar, some kind of seaweed jelly thing, and artificially to these lungs, kind of lungs, has been put a little bit less salt than in the background, and this heart has some more salt than in the background. So the measurement is done as follows. For each so-called current pattern, we choose how much electric current to put in through each electrode and how much to take out. They must sum to zero because of conservation of charge. So that's one current pattern, which I denote by cosine of theta, thinking that theta is the angle starting from zero and going all around 2 pi. So we apply these currents, feed these currents, and measure the corresponding voltages at each electrode. Then we take another pattern, this one taken from this kind of trigonometric idea, and another one, and another one, another one, until we take this one. When we have a finite number of electrodes, like in a practical situation, this is the most oscillating thing we can apply. We can't go more oscillating than that. And actually, if we have n electrodes, we have n minus 1 linearly independent current patterns, because they have to sum to zero. So that's kind of the practical way. And all of this data, I mean, the knowledge of which current pattern and the resulting voltages at the electrodes, all of this information is the data. Of course, in some other situations they are different, but here in this talk we think of collecting such data. And then the idea is to calculate a reconstruction of the electrical conductivity inside. Here's an example of the so-called D-bar method, which will be maybe the main role in my course. And then to the mathematical definition of the problem. This mathematical model was first introduced by Alberto Calderon in 1980. As you may know, Calderon was trained as an engineer, so he had always practical applications in mind. Although much of his mathematical contributions are quite theoretical, he was always very interested in practical applications, especially underground imaging using electric currents. So, in this case, we are considering the unit disk called omega. Inside the unit disk, we have a function sigma, which is electric conductivity. In this talk, I will take it to be strictly positive and bounded from above. with these assumptions, when we look at this so-called conductivity equation, this is an elliptic partial differential equation, and actually, like I just said, that we are feeding currents, measuring voltages. That's what's done in practice. Now, in the mathematical model, it's more convenient in many cases to consider this Dirichlet-Neumann map, which is kind of a voltage to current map, in the sense that F, which we apply at the boundary, is the electric voltage potential, and then the solution inside U is the voltage potential inside the domain. Minus gradient of U is the electric current field, and then, sigma times gradient of U with a minus sign would be the electric current field, and then divergence vanishes because there are no sources or sinks of current inside the domain. So this is a simple mathematical model of the situation, assuming static electric measurement, so no alternating currents, although in reality there are alternating currents that are applied. So there are many approximations between the practical measurement and the mathematical model, but in the mathematics now, let's fix this model. And now the idea is, Calderon defined this and asked, can we, if we know this one, so in the mathematical sense, if we know this linear operator with infinite precision, so to speak, is it possible to recover the picture of the conductivity? It's a really hard problem. Let me describe a little bit why it's so hard. First of all, although the partial differential equation, the conductivity equation, is a linear PDE, but the inverse problem is nonlinear. Why? Well, this is one way of seeing it. Let me define this quadratic form that actually physically this represents the power needed to maintain the voltage distribution F around the domain. So if you look at this power quadratic form, where U is the solution of the conductivity equation, then we can see that from sigma to p sigma there's a nonlinearity, because if we integrate by parts, we see that, so first of all, here, why this is nonlinear is because sigma is here and sigma is also in U because of this one. So clearly p sigma depends nonlinearly on sigma, and then p sigma is connected to the Dirichlet-Neumann map by this simple formula. So we see that necessarily the relationship between sigma and lambda sigma is a nonlinear one. So that's one difficulty. But there are more difficulties. You remember I talked about Adamard's definition of a well-posed problem, where there should exist a solution, and solution must be unique, and somehow the output of the process should depend continuously on the input. All of these fail for EIT. Let's see in what way. So yes, this was the idea, and now if our input is our noisy data and the output should be the conductivity, this one is badly ill-posed. We are failing in every respect. Let me explain. So first of all, let me talk about the unstability, the third condition of Adamard's. So let's take these two patients. This one is healthy. This one has some problem with the left lung. I'm not a doctor, I don't really know what's going on, but it looks serious, you know. So then, let me apply this cosine theta voltage around the domain. So theta angle starts from 0, goes around to 2 pi. I apply f theta to both, and I use finite element method to compute these. But these are not the ones we see in practice. This is not our measurement. Our measurement is the normal derivative of these guys. So I take the normal derivative as a function of theta, same here. So these are the measurements. Let me overlap those for you so we can see the difference. So there is some difference around the angle pi plus a little bit more. So you see, if we go around here, 0, pi over 2, pi, a little bit more than pi. In this area, we see a little bit of difference, but not so much. So then, maybe we are unlucky. Let's try another f, because we collect a lot of data. So now I'm putting cosine of 2 theta, a bit more oscillatory distribution around there. Again, we measure the normal derivatives. Let me overlap them. Well, there is some difference, but not so much. We can do this for like a Fourier series style for more and more frequencies. And you see that actually the higher frequency I take, it seems that the smaller is the difference in the data. So this is a prime example of a badly ill-posed problem, because we have two objects that are quite different. We can clearly see there's a big difference between these two. But in the data, it's a very small difference. So in EIT, in solving the inverse problem, we should give a method, and the method, when we give it the blue functions as data, it should give us this picture. But when we give the method the red curves, it should give this picture. So from little information, we should find much information. This is ill-posedness. Also, there will be noise in practical situations. Of course, with these continuous functions here, I don't know how to put the, I put some white noise on top of these guys, so you see that these little differences, they are smaller than the noise easily, so there are big problems with EIT, with ill-posedness. So we see that the forward map that takes the conductivity sigma to the infinite precision data, to the Dirichlet-Neumann map, it doesn't have a continuous inverse, even if we restrict it to the range. But then there is the other problem too. I mean, these are the spaces I use. They are quite natural for this case. So for the model space, I use L infinity over omega for the conductivities. In elliptic theory, this is quite a standard thing. The data, thinking of the typical Sobolev spaces for the H1 elliptic problem, we have that the Dirichlet-Neumann map is a linear map between these Sobolev spaces defined on the boundary. But not every map, not every linear map in this space is a Dirichlet-Neumann map. Only maybe a small part of this set are Dirichlet-Neumann maps of some conductivity. There are some results of characterization, but I would say this is not a perfect field. I would think it's safe to say that we don't have a good characterization for Dirichlet-Neumann maps to know which ones are which one. If we knew, we would project our noisy data to the range. It would help somewhat, although still there would be bad instability. But anyway, so when we have our noisy data, which is collected, like I showed you, feeding currents, measuring voltages, having a finite matrix, inverting that matrix, we can find an approximation to the Dirichlet-Neumann map as a finite, like a 31 by 31 matrix with noisy elements. So it will not be in the range. So this means that in the Adamov's case, there is no existence of solution. There is no conductivity that would have this guy as its Dirichlet-Neumann map. So we are failing the stability and the existence. Uniqueness, there are many uniqueness results in the literature based on unique determination of, I mean, if we know this perfect guy, or can two different conductivities have the same Dirichlet-Neumann map? This is, in some cases, this is quite well known, especially in 2D for isotropic conductivities. But then there is also this thing that we have a finite number of electrodes. So then you remember I talked about the ghosts in X-ray tomography. There are functions that give a zero measurement from a finite set of directions. And also I showed that when we used the SVD in the discrete case, we saw some strange patterns on top of the object, and it gave almost the same measurements. In EIT, when we have a finite number of electrodes, this is actually analyzed by these guys at A3 University in Helsinki, Finland. They assumed, actually for this theory to work, they assumed point-like electrodes. So finite number of point-like electrodes, and they could define many kinds of conductivities that give the same measurement than homogeneous background. So these are ghosts in EIT. So with practical data, we don't have uniqueness, we don't have existence, and we don't have stability. Everything of Adamar's conditions, all of them fail. It's quite a hard problem. Another thing is anisotropic, because for example, muscles like the heart muscle, I think has something like 10 times more conductivity along the fibers than transversally against the fibers. Also the brain tissue is very fibrous. In those cases, there appears anisotropic situations that along different directions there's different conductivity. This is known to be highly non-unique. There you can take any, you can take diffeomorphisms that fix the boundary, and then the Dirichlet-Neumann map will be the same. So there's quite a big amount of non-uniqueness in the anisotropic case. So it may sound that what can we do with this problem? Fortunately, there are ways to deal with it. So I will describe some methods for it. So how can we regularize this really ill-posed inverse problem? Let's see. So remember, what needs to be done is so we have this forward map, which is doesn't have a continuous inverse, not even when restricted to the range. What we need to do, we need to define a family of functions gamma alpha that are defined and continuous on all of the data space Y. And they map into X, and then they have to satisfy, we saw these couple of conditions they have to satisfy. So I will describe briefly 3 different approaches that are kind of major approaches in the literature. In variational regularization, one writes this kind of, like we did in the Tikhonov regularization, we have here the data discrepancy term. So this is sigma tilde is some conductivity, and we compare here its Dirichlet-Neumann map to the noisy measurement. And here we have, for example, this Tikhonov bound with the norm squared in the X space. And then we look for a minimizer of this functional. That's what we did also in the linear case. So we can define such a minimization problem, and then we can try to find a minimizer using an iterative optimization method. Of course, there are some problems with this because the forward map is nonlinear. So we are actually minimizing a nonlinear functional. There may be local minima. So there's such a risk. But there is some theory, actually it has turned out to be quite difficult to give a complete proof of regularization for Tikhonov, for EIT, because it's such a nonlinear case. There are some results, most notably I would say maybe the paper by Jin and Maas, which should be here, but I will add it. Jin and Maas, but these are just kind of general references to regularization theory. And also Lechleiter and Rieder wrote a couple of papers about this one where they could prove local convergence and local analysis of regularization. Then there is the direct inversion. Analyze the nonlinear inverse problem using PDE theory and mathematical analysis, and then try to design a reconstruction method and try to prove that it's regularized. I must say that the PDE-based inverse problems community has done a lot of big progress and breakthroughs in analyzing uniqueness and stability of inverse problems, or conditional stability, where there are two objects and two perfect data sets for the two objects and measuring how close. I would challenge the community a little bit, saying that actually for solving the inverse problem, finding a regularized reconstruction, something more should be even done than just uniqueness and conditional stability, which I know are usually really, really hard and long proofs to make it happen. But I think there's one more step to prove regularization, and actually there are not so many papers. There are a huge number of papers about uniqueness, but so far I think these are the only papers I found analyzing direct nonlinear inversion methods in the sense of regularization strategy. I would say Professor Ikehata is a true pioneer in this respect, quite early already proving such regularized methods. But this is, I think, there's a lot of work in this area to do. So lots of open problems, very interesting mathematically, also very important for practical imaging. Then there is that really big and very nice and powerful methodology of Bayesian inversion. In this course I will not touch it, it's a big topic of its own, and I decided to concentrate on the first two ones. But this really is a really good and strong methodology. I recommend the book by Jari Kaipio and Erkki Somersala about it. There the idea is to, in our measurement situation, to define or to treat m, f, and epsilon as random variables, random vectors or random functions. And then look at the posterior distribution, the conditional distribution of the unknown f on the condition that our measurement is the m that was given by the machine, whatever our measurement machine is. And then we come at Bayes' formula, where here we put all a priori information about our unknown. This is a probability distribution that should give large probability for kind of expected or kind of typical f. Whatever we know about f, we put here. This one is actually a measurement model. This is very similar to the data discrepancy situation. So this gives a high probability of pairs of m and f where the measurement m comes or is very close to the measurement coming from f. And then once this is written, what remains is to do completely well-posed statistical inference from this distribution. So it's kind of a complete solution of the inverse problem. It describes all the ill-posedness and everything, although it also leads usually to quite heavy computations. So let me summarize in a nutshell a little bit these three approaches. In the Tikhonov type variational regularization, it's nice because when you write the code, for example, like the Gauss Newton code we will look next, then you have to change the forward map a little bit and change maybe the prior, but anyway your optimization machinery stays the same. So in the same framework you can attack many problems. Then they are iterative. Usually when you practically find the minimum, usually it's done by iterative methods because of nonlinear functionals. So the direct problem model, there needs to be a computational model for the direct problem, like we had for the X-ray tomography. And sometimes the model is very heavy computationally, like a big finite element mesh and take time to solve. So this is kind of a minus sign because there may be many direct problem solutions. And also there is the trouble with possible local minima, which you don't even know. If you end up in a local minimum, there is no clear way of knowing if your result is local or global minimum. So it's kind of a often, I must say though, often this method gives good and useful results anyway. But from a kind of a completeness point of view, it would be nice to know that it's a global one. Well, then the direct nonlinear inversion, where I have worked the most in this area. As I will show, we can deal with the highly nonlinear EIT that has proved really difficult for this methodology to cover. With this one, we can cover it. But then, after a lot of work, there is a regularization strategy for one problem, EIT, and it doesn't give a strategy for any other problem. So it's also kind of labor intensive in that sense. Bayesian inversion is nice. It's very flexible. All kinds of prior information can be easily put in. It also, if you use Monte Carlo Markov chain methods to sample the posterior distribution, it will also give some quantitative estimates for uncertainty, how reliable the result is. But it's really tough computation usually. Okay, so in this course next I will talk a little bit about this one, and then I will talk a lot about this one. Any questions at this point? If not, let's continue to the second one. And let me mention that I already put all my slides to my homepage, including this one, and until the end of the course. So, especially the part on the D-bar method for EIT, there are some quite technical parts. So, if you want, you can download and have the slides. I've been talking about that approach for about 20 years now, and still I haven't really found a good way to approach all the technicality in that one. But let's see, maybe future will bring a solution to that. Okay, so next, let's see how the variational regularization works. And for this one, we also have today a computational session. Janne Tamminen will show how to compute with these methods. So let's see what it's about. So the basis is the Tikhonov regularization we already discussed in the linear case. So now we do a bit more general than we did in the linear case. Namely, well, first of all, this f now can be a nonlinear function. And here we don't have only the x, only the norm of x squared, but we have a little bit more. So we have here some x star that maybe we know a priori that the conductivity or whatever in our problem is. If you know something, it's roughly something like this. So we can penalize that. Please don't be too far away from this one, because this is roughly right. And this L, it can be the identity, or it can typically be like a first order or second order derivative, like a finite difference derivative. Then it will favor smooth solutions. Then you could also have like a discontinuous guy here, and then the difference between x and the discontinuous guy must be smooth. There are many tricks that you can do, and actually these can also include directed derivatives and even kind of some geometric information. If you know some interface location, you can, for example, say that over the interface there shouldn't be smoothness, but along the interface it must be very smooth. So this way you can have some edges also in the reconstruction. So it's actually quite, although it's not really much more general than before, but it's anyway, it gives quite many possibilities even with this one. So I'm now talking about just a discrete or finite dimensional case. So x is a vector in Rn. F maps Rn to Rk, possibly nonlinearly. Oh well, it's a nonlinear part of the course, so we assume this is nonlinear. M is the measurement. This one we know a priori. Alpha, again here, a positive real number. And yeah, I think I covered this one. So then, There are many ways of doing it. I will talk about pretty much the simplest approach one can take. So let's just use the Taylor theorem, approximate at some point x tilde, near x tilde, let's approximate the nonlinear map by constant plus linear term. Use strong ideas going back to Newton. So then we take the Jacobian, and let's minimize this functional where now we put here, instead of the full x, we put this approximation. So then we would like to differentiate this one. So let's see what happens. So let's compute a little bit. Let's remember that when we differentiate this kind of expression, we will get 2 times ata x minus 2 times ATB. And then when we start computing and we add and subtract some terms, we see that the gradient will have this kind of a form where it appears, the Jacobian appears in this form, the regularization matrix appears also in this L transpose L form. We also have the transpose Jacobian here, acting on the difference in the measurements, virtual measurement and the actual measurement, and then that kind of a term there. So then, at the minimum, we would like the gradient to be 0, and if this guy is invertible, we can find the way step to the minimum. So this leads to the Gauss Newton iteration. 2 pretty strong guys behind it, and we'll see it's actually quite powerful how it works, even for the nonlinear case of PIT. But this is how it goes. This is the iteration. So the next iterate is done by having the previous iterate and changing it with this term. We need to invert such a matrix. Here we need to solve the forward problem for the iterate. So this may be expensive. For this one, we will use finite elements. And usually, well, this kind of thing is usually quite fast to do because those matrices can be pre-computed. And of course, in the finite element solution of this one, also we can pre-compute many things. Okay. So then, let's take a closer look of the forward map of EIT, and this time this will be a more practical view than the before. I showed these like Fourier modes, that's called the continuum model of EIT data. But now let's take a more practical view of the so-called complete electrode model. So you remember this situation, we have a finite number of electrodes and we are feeding the currents and measuring the voltages. So the same situation still. And now we need to discretize everything. So for the conductivity needs to be in Rn because our forward map maps from Rn to Rk. So we make a finite element mesh, and in each triangle we have a constant value for the conductivity. So our number of triangles is n, and we have this kind of piecewise constant approximation where key is the characteristic function of a triangle. So this is the discrete conductivity, looking maybe something like this, like in the software package that Janna will show later today. This is the mesh that's used there, so not very fine mesh to make the computation really quick. Oh, sorry, what did I see there? Okay, yeah, so same, yeah. So then, when we are given a vector in Rn, we will interpret it as this piecewise constant conductivity, and then we should compute this vector, which should be the measurement data. So let's see what happens. So let's take L, the number of electrodes, and then we can have L minus 1 linearly independent current patterns. So those we will all apply computationally now, because of course we have the data from the machine, but now computationally. So one by one we take the current pattern, we put it into the complete electrode model, which I will explain next. We read out from the complete electrode model the voltages at the electrodes, and actually there also we have L minus 1 here. There are a couple of ways of doing this. Actually, I think in the official definition of the complete electrode model, I think the solution of the Neumann problem is made unique by adding a constant that makes the boundary a Dirichlet value to be 0. Although now it's just a sum, so some of these guys will be 0. Here I'm kind of thinking that we choose one electrode to be the ground electrode and record the differences to the ground electrode. So then we would have L minus 1. If we do the subtraction to the mean 0 voltage vectors, then we do have L voltages, but only L minus 1 linearly independent possibilities. Anyway, so then we collect all of these from each current pattern, all of these guys into a vector, which will then be the output of our forward model. So what is this complete electrode model? Let's take a look. So now in this unit, this case, what we do is we assume there are L electrodes. In this picture I took 16. So they are just subsets of the boundary, intervals like this along the boundary. Finite number of them. Between them there is a gap. And of course there's a choice here. How big is the electrode and how big is the gap? There are some theoretical results that say that for best imaging results, the electrodes should fill as much as possible, like you saw in the RPI tank. There was a little piece of rubber between big electrode plates. And then there still is the H1 solution of the conductivity equation. And now the boundary conditions are more complicated. So we have these disjoint sets I just showed you. They are subsets of the boundary. There is L of them. And first of all, in the gaps between the electrodes, there is no current. They are insulated parts. Then at the electrodes, there is a Robin condition where there is a U voltage. This is the current through the boundary, or these should, well, yeah. And here are contact impedances that model some, there are some chemical situation, especially if there's a metal on human skin, there will be some chemical things happening. There is sweat and some stuff, and the contact is not perfect. So actually, these kind of numbers here are needed for more accurate modeling of the measurement. And actually, these are also unknown in the inverse problem. So today we will assume these are known, but in practice they are not. So they should also be, although they are not interesting, but sometimes they have to be left as degrees of freedom in the problem. And then the current pattern is understood like this. So at each electrode, the integral over the electrode of the normal derivative of U equals this one. So this is the total current integrated over the electrode, because it's not a constant function actually. So we integrate over it and it has to add up to this one. So this is the complete electrode model. And as shown by Erkki Somersalo, Margaret Cheney, and David Isaacson in 1992, these stars here are the actual measurements they did at the Rensselaer Polytechnic Institute machine. And they show that if there's no modeling, there's something like this, and with something discrete, not so good, lumped Z. This is the shunt model that doesn't take into account all the details I just showed you. So really this complete electrode model is the most accurate model so far available for these measurements. And it seems that it's good enough model for EIT measurements. And then there's a special variational approach to the complete electrode model. There's a little extra compared to the standard theory of elliptic PDE, where you would have just the function inside the U, and then in the variational form you would have something like this. But now there's something extra related to the U at the boundary. So it's H1 in omega, so the Sobolev space of functions inside, and then it's a direct sum with RL, because there's this U number at each electrode. So this is the variational form, looks like this, and then we say that this is a weak solution to the complete electrode model, so it's a pair of an H1 function and a voltage vector if this variational form equals this one that contains the currents here. That's the variational formulation in the continuum, or for the U function, it's a continuum model, but then we use finite elements to discretize U. So it's just a standard way to take a triangularization inside the domain and then consider this kind of pyramid-like functions where the value here is 1 and at all the other vertices the value of the function is 0, and in each triangle it's piecewise linear. It's inside each triangle it's a linear function. So then you see its support is the yellow one, and then it's this kind of a like pyramid-like basis function. So then they make a finite dimensional subspace of H1, because these guys belong to H1, and then actually we can look at pairs in this space. So this is the finite dimensional approximation space, just a subspace of H1 but finite dimensional. So then we can look at the same form in this space, and this is how the finite element method works in this case. So then the potential is of course represented by a sum of those basis functions, and one way of dealing with the vectors of voltage is, for example, to take such a basis for these vectors. And then the finite element method goes into this kind of situation, so just a matrix equation where the matrix contains 4 blocks, where the B block is dealing with the interior functions only. The C block is kind of interaction between the interior functions and the voltage vectors, and then the D part is just interaction between the voltage vectors. So this is how to construct the matrix A. And for these ones need to be computed for all pairs of basis functions, but there actually many of them are zero, because if there's a basis function here and here, they are just, their supports are not overlapping at all. And then for this guy and this guy, there's an overlap of support, so there's a non-zero function to be integrated only inside this part. So it's a programming task to go through all these pairs and see if there's intersection, and if there is, then integrate. This kind of thing. And also, after some computations, it can be seen that also for the Jacobian matrix, it also boils down to computing this kind of integrals multiplied by this one. So and then we go back to the Gauss Newton. Now we have all parts there. I described how to solve this one using the complete electrode model. So it gives out the U voltages corresponding to all the current patterns, and this is what we measured, let's say, in a huge vector, and this gives a simulated vector. And then the Jacobians were also computed in the finite element approximation. So then we can just start running this one. And one example is, so in the computational approach that Janne is showing, it's actually code written by Marko Vauhkonen from University of Eastern Finland in roughly the end of the 90s. It's a classical piece of code. So there you can choose a center point of a disk and the radius, and the disk is a bit weird shape because of the triangle approximation, and then you can compute the regularized solution, and you can choose the regularization parameter. Janne will show you how all of that works. That's kind of the basic variational approach, going through modeling of the forward problem and building up the basic Gauss-Newton iteration scheme. Any questions about that stuff?
How is the initial value of the iteration is the initial values?
Yes, excellent question. Of course, the initial value makes a difference. There can be local minima if you choose a really bad one, and maybe the iteration also if you choose a really bad one. I don't know, did you really collect some intuition about this?
It works surprisingly well with all kinds of initial values.
Yeah.
So, but I cannot say anything different.
Yeah. So it seems to be pretty robust. Yeah, myself, I don't have really a deep experience with these things. I've been always working with EIT with the direct methods. So this is, for me, this is something I have seen many times, and kind of this is how it goes, but I don't really have the good like practitioners grab on this approach. But yeah, I remember also asking some people about computing with these, that do you have problems with local minima? They said that yes, they sometimes have. So that gives me an impression that it's important to choose a good initial point. Other questions? If not, let's then go to the world of direct inversion for EIT. So I will show you the definition and properties of the so-called complex geometric optic solutions. I'll show you how they can be used to define a certain nonlinear Fourier transform, which is kind of tailor-made for Calderon's problem. And then in the end, depending on how, probably tomorrow, I'll then also show a new use of these complex geometric optic solutions, just submitted this year, how we can then connect it with the radon transform and see edges and singularities in conductivities in a new way. Okay, so this is the structure. So I thought that first I talk about the classical D-bar method, with first the complex geometric optics solutions, and then I show you how to prove that we can get a regularization strategy out of it. Then I will talk about how to numerically implement the D-bar method to get images, and then I'll describe a little bit what has happened in the research of this topic in recent years. And then this part is really for the seeing these, seeing the wavefront set of the conductivity from the measurements. Okay, the first part, the regularized D-bar method, is a joint work with David Isaacson, Kim Knudsen from Denmark, Matti Lassas, who works at the same department than me in Helsinki, and then John Newell from RPI as well, and Jennifer Mueller from Colorado State University. Well, this is the same that we saw before, the same definitions. So let me skip that one. Let me first give you, in a nutshell, the idea how this D-bar method works. So behind the D-bar method, there is the fact that there is a nonlinear Fourier transform, which is a complex valued function in complex plane. So we can go from the image domain to the transform domain, and there's also an inverse nonlinear Fourier transform. So we can go back and forth between the domains. And then Adrian Nachman, who is currently in the University of Toronto, he showed in his 96 Annals of Mathematics paper that if you know this one, the infinite precision data, you can solve a boundary integral equation and use the results to compute this guy in the whole complex plane. And then apply this one and you will get the conductivity back. Then we tried, in our team, what happens if we take the finite measurement matrix of EIT and we put it in a numerical solution method of the boundary integral equation. We try to compute the nonlinear Fourier transform in the complex plane, and then we apply the inverse. So we saw that something like this happens. There seems to be a stable area around the origin in the complex plane where we get the good values for this one. If I go back to the previous one, and now I jump back here, you see that in the middle the colors stay the same, but outside here these white values mean that they are either very positive or very negative, so they kind of glow up in some areas. This is actually the ill-posedness of EIT showing up in this way. So then we did a kind of a basic engineering approach. We cut away the bad part, just put 0 outside, and then apply nonlinear Fourier transform. And then we found out that we get these kind of images that are kind of blurry, but however, they are robust against noise. I mean, if the measurement noise is even bigger or changes, this one doesn't change so much. And this is what regularization aims to do. I mean, even if there is noise in the data and all the ill-posedness, no existence, no uniqueness, no stability, still, if there's a regularization strategy, we can get an approximate image which is robust against noise. We found out that yes, this is the case actually. Our first results were in this paper in 2000, and then in 2009 we could provide a proof that this is a regularization strategy. So this is kind of the overall picture what's going on. This is quite a very, very nutshell history of the literature about this topic. Ludwig Fadeev, who actually died this year, a Russian mathematical physicist, he wrote about these complex geometric optics solutions in his 1966 paper, which was maybe not completely rigorous mathematically, but the idea was there. And then John Sylvester and Günther Ullmann brought this idea to the rigorous field of mathematical inverse problems. They defined the CGO solutions and they were able to use them to show uniqueness in three-dimensional EIT, in isotropic case. Then, regarding the D-bar method, these two papers in 1988 contained the steps of the D-bar method and described them, but they could only work in dimension 3 and higher for technical reasons. Then this is a big breakthrough paper by Adrian Nachman, where he could do this reconstruction in the 2D case, and this is actually based on a proof of existence and uniqueness of the complex geometric optic solutions. In 2D, up to this point, no one could prove anything about their existence and uniqueness. But here was a breakthrough showing that in the case of EIT, they are there and they can be used. And then later in our team, we went on and tried this numerically, first in a simple way, and later in a full way. Here we tried it with the human data and found out that it works. And here we could prove the regularization strategy property. So then, let's go to the mathematical core of the whole approach, namely these complex geometric optic solutions. And I will talk about the CGO solutions related to the Schrödinger equation. There are also other variants I will describe a little bit later, but this is the thing that works in the standard D-bar method. So let's look at the Schrödinger case. So here the idea is kind of a mathematician-like to go from the conductivity equation to the Schrödinger equation. So physically it may be a bit strange, but mathematically let's not care about the strangeness, let's just change equations. We can define such a function q in the plane with this formula using our assumptions on sigma. So actually we have to assume two continuous derivatives in sigma, or Nachman assumed two weak derivatives, but let's assume two continuous derivatives in sigma to allow for this Laplace, and assume that sigma is bounded away from 0 so that we don't divide by 0. And then also let's assume that the conductivity is constant 1 in a neighborhood of the boundary. So then q will be a nice continuous function that we can 0 extend to all of the plane. So then we actually have q in C0 of R2 actually. And then let's look at this Schrödinger equation. So we have minus Laplace plus this function defined in all of the plane. And then we look for special solutions of the Schrödinger equation parameterized by a complex number k. In this case, let's take just non-zero k. The idea is to try to find exponentially behaving solutions. In this technical sense, psi should satisfy this requirement. So see what this means. So if psi would be equal to the e to the ikz with a plus sign, then this product will be just 0, and then we subtract 0, and of course the 0 function will belong to this Sobolev space. However, psi will not be exactly e to the ikz, it's just asymptotically according to this formula. In this case, actually this Sobolev exponent here is over 2, and by Sobolev embedding, these are continuous functions, and of course they have to have some kind of decay at infinity. So psi in this technical asymptotical sense is close to the exponential function e to the ikz. And here by ikz I mean this complex multiplication. I will all around the talk I will actually equate z with x plus iy. Okay, how to construct such solutions? So I follow here Nachman's technique. So he gave a name to this e to the minus ikz times psi, which is a function somehow close to the constant function 1. Let's call it mu. And then we see that mu satisfies this PDE. So actually there is this first order extra term, and this d bar operator is this one. So mu satisfies that one, and mu minus 1 should belong to this Sobolev space. So then actually Nachman used scattering theory in a mathematical way. This is a non-physical scattering situation, but anyway, there's a Lippmann-Schwinger equation like this. So we have mu here, and this gk is the fundamental solution for this operator. So if mu satisfies this equation, then this property and this property will be fine. That's the way to try to find mu that satisfies this one. Let me just show you a picture of the fundamental solution of Fadeev. This is the real part, this is the imaginary part. In MATLAB, because MATLAB has built-in special functions, it's actually quite convenient to compute this G1 function. And if we have G1, you will have Gk for any k by this property. So then, here is the technical trick, technique in all of its beauty. So we want solution of this one satisfying this one, so that we construct mu minus 1, which is an element in the Sobolev space, by applying this inverse operator to this guy. A short computation, if you apply this one without the minus on both sides, you will quickly compute and see, and that's what you get, the desired solution. And also the function spaces have to go right here. So Nachman proved that pointwise multiplication by Q is bounded, a linear bounded operator from the Sobolev space here to LP. Q itself is in LP. These are in infinity actually because of the continuity. This one maps compactly from LP to this Sobolev space. So then it actually follows that this here is a Fredholm operator of the second kind. So it's identity plus compact. And also this function here belongs to the correct Sobolev space. So then everything boils down to proving that this operator should be injective. And this is Nachman's big breakthrough using the theory of pseudo-analytic functions in the sense of Vekua. He could prove using kind of a generalized version of the Louis Liouville theorem from complex analysis. Generalization of Liouville theorem he used to show that there is a unique solution, that this is injective for any non-zero k. And actually, so this was the first breakthrough to show for any class of potentials Q that this guy is an invertible operator. Beforehand, there were many works on the so-called Novikov-Veselov equation that uses the same CGO solutions, but the authors couldn't. They always assuming that there are unique CGO solutions. They didn't know. Nachman was the first one to show, and the proof really needs that the Q is of this form. It really essentially uses it. At this point, I would also like to point out that in the recent couple of years, there are some new results extending Nachman's result. For example, the paper by Michael Music, where he uses the trichotomy of Professor Murata Minoru, who is now, I think, retired. In his 1986 paper, he divided Schrödinger potentials into three classes: subcritical, critical, and supercritical. It turns out that these are very crucial for this case, namely for supercritical potentials there will be k values that this is not invertible. These are called exceptional points. Nachman showed actually in this class of conductivity type, actually it turns out they are the critical ones, which is kind of a very small set of potentials. And now Michael Music extended this result to subcritical. So this is also invertible for all subcritical potential, which is really a big set. So some that kind of developments recently. Okay, but in this context, now that we know by Nachman's theorem that we have unique CGO solutions that we can use, so then let's define our nonlinear Fourier transform. This is what it is. It's called T of k. It's a function from C to C, and it's defined like this here. Here is Q, here is psi, the solution that exists uniquely, and here is some exponential. Why it's called nonlinear Fourier transform? Well, if you put here instead of psi, just to the e to the ikz, and make a little computation, you see that actually it's the usual Fourier transform of Q. But psi really is not equal to e to the ikz. It depends on Q via the Schrödinger equation. So this is nonlinear because Q is here and Q is also here. It is possible to compute this nonlinear Fourier transform from the electrical impedance tomography measurements. Here is how Nachman showed how that goes. This is the boundary integral equation I mentioned before. These are the solution of this one is the trace of the CGO solution at the boundary of the domain. The trace solves this equation where here is the exponential restricted to the boundary. You see here is the measurement data. Here is the measurement data corresponding to homogeneous conductivity 1. It's quite innocent here. In practice it causes some problems because if you're measuring a person with EIT, this is what you get from the measurements approximately. But for this one you should have another person of the same shape but homogeneous inside. So there's some practical difficulty of dealing with this one. But anyway, now mathematically it's a perfectly fine operator. So we have this here, this SK, mysterious SK, is just a single layer operator that contains inside Faddeev-Green's function, which is actually just the previous fundamental solution we saw multiplied by the exponential. So actually this capital J K is a Green's function for the Laplace operator. But it's not the usual one. This has exponential growth to some directions. So it's kind of an unusual one. But it's used here in the single layer operator here that acts on functions defined at the boundary. And then actually this nonlinear Fourier transform can be computed with this formula, taking the trace, the solution from here, put it here, use both of the data operators another time, and just integrate over the boundary, and this is T of k. This computation follows from a formula of Giovanni Alessandrini, who is based in Trieste. And then this D bar, why is this called the D bar method? This is actually an observation done by Beals and Koifman when they studied nonlinear evolution equations. As you may know, the famous KdV equation, the Korteweg-de Vries equation, which is a nonlinear wave equation in dimension 1 plus 1, it can be solved by taking the scattering data, quantum scattering data of the wave. I mean, it's also very interesting. There's a water wave described by the KdV equation, and then if you take the quantum scattering data of the water wave and evolve that one in a linear, very simple way, and then use inverse scattering, you will get the water wave at a later time. I think it's quite amazing breakthrough Vincent Koifman was studying the same kind of equations in dimensions 2 space dimensions plus 1 time. So kind of similar equations to KdV but in higher dimension. So they found that these CGO solutions satisfy such a d-bar equation. So here the thing is to ask if these solutions we constructed that depend on the complex parameter k, I think it's natural to ask, are the parameters analytic in k? So you apply this one, because for analytic functions it will give 0. So the Cauchy-Riemann equations packaged into one operator. But what happens is not 0, but something like this, where the solution itself appears here, and then some multiplying function. So this is like a pseudo-analytic function in the sense of Bequa, but nicely the nonlinear Fourier transform appears. So then in the inverse Fourier transform part, when we know T of k, we can solve this d-bar equation and get mu, and from mu we can get the conductivity back. So it's a bit like magic, I think, this whole very, very magnificent, in my view, how this works. So then let me also tell a little bit about how to computationally evaluate these CGO solutions. They can be used in many things. This EIT imaging, also for the so-called Novikov-Veselov equation, that's a direct generalization of the KdV equation. It can be solved also by this nonlinear Fourier transform. So actually, Gennady Vainikko, an Estonian mathematician who worked in Helsinki, he designed a fast solution method for the Riemann-Schwinger equation, which turned out to be really good for solving these kind of equations we have here. There was first, I did in my PhD thesis, quite simple and slow computational method, which we soon made much faster by Vainikko's method. And also let me comment that this team in Denmark, they also did this in 3D. So let me explain how to compute solutions. So we'll need to solve this one, where the convolution here can of course be written like this. And note at this point that in our case Q is always compactly supported, just supported inside omega. So actually this integration here is only over omega. That will help us in a minute. So now what we do first, following Vainikko's approach, we take the unit disk where Q is supported. Actually we take the disk of radius 2 and we take a square here so that there's a little bit more space in between being here. So this is the square, this interval squared. And then we define a truncated Green's function. So this and periodic, we make everything periodic. This is in Vainikko's, the basic idea in Vainikko's method. We tile the space with these squares and start to think about periodic functions. So now we truncate our Green's function with such a truncation function that equals 1 inside the disk of radius 2 and a little bit more as well. And we copy this guy to every square in the periodic plane. And then we can define periodic convolution, where actually this integration is not over the R2, but it's over the torus. So now we actually, instead of this equation, which is defined in R2, we actually look at this equation, which is defined for periodic functions. And now, the nice trick about this is that first of all, the periodic equation has a unique solution by Fredholm arguments. For uniqueness or injectivity, we can use the full space situation actually to show it. The solution of the periodic equation coincides with the solution of the full plane equation inside the unit disk, because the Green's functions are equal up to 2. Because when you look at the convolution, if z and w are both inside the unit disk, then z minus w is inside the disk of radius 2. So it's actually the same value of the Green's function there. And we can actually see this by constructing, looking at functions like this that have the periodic solution inside, and then we actually use the full space Green's function to define such a function in all of the plane. And after some computations, we will see, because of uniqueness, it has to actually be this one. That's somehow the trick how this goes. But the main idea really is that it's enough for us to solve the periodic equation, and when we get the solution of that one, we can put it here, because the integration actually is only over the unit disk. And because they coincide, then actually we get mu everywhere, if we know the periodic solution only in the unit disk and put it here. So for the periodic, solving the periodic equation, what we do, we take such a grid which is very much suited for the fast Fourier transform. So the origin is always included in the grid, and well, this is the MATLAB way of building up the FFT grids, that from the left side we have a power of 2 points here before the origin, and then we have also another power of 2 here. So we construct such a grid inside here, because with FFT, the fast Fourier transform, we can implement the periodic convolution, or the convolution over the torus, in a very fast way. So then, what we do, we number these points in the MATLAB fashion, column by column, and we represent our periodic functions by just the finite number of point values at those points. So actually, our solution will be represented as such a complex finite vector. Then we build up this kind of little algorithm that given a phi, given an iterate phi, so these are the values of phi at the grid points. Here we multiply it by the q pointwise at the grid points. Here are values of the Green's function at the grid points, except at the origin where it has a singularity. Then we just put 0 here. It's weakly integrable anyway, so it doesn't make a big difference here. When we refine the grid, the error caused by this one will go to 0. So then, this matrix we FFT, and this matrix we FFT, we multiply them together pointwise and inverse FFT. This is convolution. And then this one comes here minus sign. So this is actually implementation of that operator. And then, so the idea is, so this is what we want to solve. On the right hand side is just a vector with 64 elements and all elements 1. This is the unknown, and we need this operator computationally. That's this one. And then we will give that operator, for example, to GMRS. There are these iterative solutions of linear equations that only need an algorithm that applies the action of this linear map to the given vector. They are based on so-called Krylov subspaces, where you have these bigger and bigger dimension subspaces. You start with just one dimensional, with just B here, then and then you look at the least squares solution inside that subspace, and then you add another one, another one, and in every case you just need to be able to apply your linear operator, not necessarily constructing the matrix, but you just have to know what is the output of your linear operator for one given vector. It's based on that kind of approach, so then iteratively the solution becomes a better and better approximation. So that's how we can compute these CGO solutions. Actually, this is not needed in the inverse problem at all. This is mainly needed for computationally studying these CGO solutions and computing these nonlinear Fourier transforms for testing purposes. But for the solution of the d-bar equation, which we will need in the inversion, actually it uses almost the same thing than here. In the remaining time, maybe let me quick show what's going on with this one. So we should construct the regularization map. Construct these guys and prove that they have the right properties. Namely, in the case of EIT, so we should define these continuous mappings from data space to model space, parameterized by a regularization parameter. And again, like before, but now in the nonlinear case, in the case of EIT, so for a given sigma in the domain of the forward map, which I will define in a minute, for fixed sigma, if we have infinite precision data, we should get zero error in the limit when alpha goes to zero. This is basically Nachman's proof, actually. It will come from there. But what to do with noisy data? Again, sorry, this was delta previously, now it's epsilon. So anyway, we should choose alpha as a function of the noise level. So in this case, I have epsilon denoting the size of the noise. So somehow we should choose alpha for a given noise level. First of all, so that alpha goes to zero when epsilon goes to zero, and then again this one, the worst case reconstruction error. So this is the reconstruction error for a given alpha. And if we take the supremum over all data in the disk of noisy data with radius epsilon, this should go to zero. And this is how it all works. On the left-hand side column is Nachman's proof in a nutshell. Missing some parts, but I mean the core parts are here, and this is what we have to do to make it regularized. So this is for infinite precision data. If you really know the Dirichlet-Neumann operator, so Nachman showed that you can solve this boundary integral equation for any non-zero k. So you get the traces of the CGO solutions. Then you can put the trace of the CGO solution into this integral over the boundary, using again the two pieces of data. So they are also here and they are also here. And then you get the nonlinear Fourier transform, which you can plug into the d-bar equation. And Nachman showed that this equation has a unique solution with these asymptotics. And then actually Nachman showed that if you take k to zero, you will get the square root of the conductivity. So the conductivity comes out of the equation there. Maybe I have a quick comment about that one, because it may look weird. But it comes from here. Very hand-waving proof. If you take k to zero in this equation, this one will disappear. You get zero here. And then q has this form containing square root of conductivity. So now, if you just take k to zero here, here is k0, then you can ask, what is the function you should put here that is 1 asymptotically at infinity and satisfies this equation? Well, if you put square root of conductivity there, it will cancel this one, and this will give Laplace of square root of conductivity with a minus sign. So it will give 0. So this is an extremely hand-waving proof. Why do we get the conductivity back from the mu functions by putting them to 0? So this one. But then, when the data is noisy, and the noisy data is not even a Dirichlet-Neumann map of any conductivity. So in our paper, we had to show that this boundary integral equation is still solvable, but not for any k anymore. It's for non-zero k, but smaller than some radius. Like you saw, there was a stable area near the origin in the complex plane for noisy data. So actually this R is directly computed. Oh, no, it's again delta. Oh, sorry about this one. So the noise logarithm of the noise level will give this truncation radius very directly, actually. Then outside that disk, let's put the nonlinear Fourier transform to 0, and inside the domain, let's compute it by this integral using the solution from here and the noisy data again here. So then we get this noisy TR inside the stable disk. Then we should solve this one, but now we actually have a benefit from our truncation in the nonlinear Fourier domain, because this guy is now supported in the disk of radius r. So this is compactly supported. We can again use the periodic trick of Weinikko's method to solve this numerically, and also, I mean, analyzing this one becomes also nice because this is supported in the disk of radius r. So we can solve this one both theoretically and numerically, and then I will define our regularization strategy so that I will take the solution of this one and put k to 0. So it's completely symmetrical to here, and actually what happens here, this 1 over r will be the regularization parameter. Also here you can see what happens when I'm using more and more noise, bigger and bigger noise. We have to truncate more severely, and then we are low pass filtering our results more and more. So this is somehow how the ill-posedness comes into the play and how the regularization is done. If you need to regularize more, you take a smaller if you regularize more, you need a smaller radius, which also means bigger regularization parameter alpha. So there's a direct connection here, and like we had to have here that alpha goes to 0 as epsilon goes to 0. We have it because we have it with R depends on the noise level in this way, and then the parameter is given by this. Okay. So I think we'll go to the proof tomorrow. Thank you very much for your attention.